So in this video, I want to go over a bunch of common antiderivatives, which will be helpful in evaluating integrals. Okay. So generally when we're doing this, we're just kind of trying to think backwards from how we thought about derivatives, which is what function can I take the derivative of to get this function, right? So let's look at like a table of f of x values and capital F of x values, which is the general notation we use for antiderivatives. Okay. So, for example, what if we have a constant like c, where c is a constant, okay? Then the antiderivative of that is going to be c times x, right? Because the derivative of a constant times x would be the constant. And it's important to note when you're talking about antiderivatives, you're really talking about a family of antiderivatives where we could be adding any constant. And for that constant, we typically use a capital C. Okay, so we'll put plus capital C on the end of all of these. Now, these don't pop up in the definite integrals. Okay. You know, the reason being that if you're doing f of b, capital F of b minus capital F of a, those constants would just cancel each other out. So they don't appear, right? But they are important in other contexts, like when we're doing the indefinite integrals. Okay. So I'll write plus c for all of these right now, but you know, when we look at definite integrals, they won't pop up there. So what about just like a general power function, right? Like x to the n. This was one of the most common derivatives that we do. So what about its antiderivative? Well, this is going to be x to the n plus 1 over n plus 1, and then of course plus c. So we can easily show this. We could do d dx of x to the n plus 1 over n plus 1, and we're going to get n plus 1 over n plus 1 times x to the n. These cancel, and we're left with x to the n. Okay, so we can confirm that this is indeed the antiderivative of x to the n. Okay. Now, one important exception to this rule would be if you had negative 1, n equals negative 1. Why wouldn't that work? Well, take a look at the denominator, right? You would have something divided by 0. So we do need to look at that one as a separate case. Okay, so if we do x to the negative 1, in other words, 1 over x, the antiderivative is the natural log of the absolute value of x plus c. Okay. So first of all, why do we have an absolute value in here? Well, there's nothing stopping 1 over x from being negative, right? So we the natural log requires your inputs to be positive, right? The domain is 0 to infinity. So we need the absolute value in there to make sure that the values in there are indeed positive. Okay. And then you might remember that the derivative of the natural log function is 1 over x, right? So that part of it might not be too surprising. Other special functions, e to the x, right? As we might expect, the antiderivative is e to the x. In general, if you don't have e to the x, if you have like 2 to the x, the antiderivative is 2 to the x over the natural log of 2. So that's because the derivative of 2 to the x is 2 to the x times the natural log of 2. Okay. Let's see, sine of x. The antiderivative of that will be negative cosine of x. So the derivative of cosine of x is negative sine of x, so those negatives will cancel. And then the antiderivative of cosine of x then will be sine of x, a positive sine of x, right? Because the derivative of sine of x is cosine of x. There is one special trig function that I do want to mention because it is kind of a strange one, namely the antiderivative of 1 over 1 plus x squared, which is a fairly common form of function, is arctangent. Okay, so just something to keep in mind. We didn't talk about arctangent much in Math Tools 1, but this is just kind of a weird coincidence where this is kind of a not too uncommon form of function that pops up with this trig function as the antiderivative. So I guess now we can just take a look at just some examples of finding antiderivatives. So I'll just kind of go through a bunch of them. Okay, so if we want to find the antiderivative of something, the way that we usually write it is with the integral sign without any limits of integration. So this is called an indefinite integral because a definite integral has the limits of integration and this does not. Okay, so this just means to just find the antiderivative. Okay, so if we find the antiderivative of x, for example, with respect to x, so this always just says what our variable is, then this is going to be equal to x squared over 2 plus c. And this is because of the power rule for integrals, which was x to the n plus 1 over n plus 1. So n here is 1, so this is x to the 2 over 2. The integral of 5 dx would be 5x plus c. Okay, so technically you can think of this also as a power function with x to the 0. So it becomes x to the 1 over 1. So same thing using the power rule. The integral of 5x to the 4th plus 4x to the 5th. Again, we're using the power rule here, and our integral properties told us we could take the integrals of these separately and also ignore the constants in front. So if we want to be technical and write the whole long thing out, we can find 5 times the integral of x to the 4th dx plus 4 times the integral of x to the 5th dx. Okay, and then these are just using the power rule, you can find these. So 5x to the 5th over 5 plus 4x to the 6th over 6 plus c. So notice that even though I have two integrals, I'm only writing one constant. We're not specifying what the constant is. So you could take the constant of the first one, add the constant of the second one, and just call that the new constant, right? We're never specifying what it is, so it doesn't really matter. So you could simplify this a little bit, of course, if you want to. So x to the 5th plus 2/3 x to the 6th plus c would be our final answer. Okay. Now, some of these, you might immediately run into some trouble and they might not fall into one of these rules properly. So there will be a lot of different techniques we can use in order to evaluate some of these that we'll explore as we go on with these videos. But for now, this gives us a good tool set to evaluate kind of a broad range of functions. Okay.